we have the fifth final talk of André Assis on his mini course.
So, thank you, Joa. And as Guy said, congratulate you to organizing this wonderful school here, Mathematics Institute at UNICAMP in Brazil. Very nice indeed. And I also hope that our collaboration will continue and will fructify. So today, until yesterday, I was talking about the works of Ampere and Weber. Now I will speak about my own work, not something that Weber did, but it has connections with Weber. So that's what I call relational mechanics, and there's some fascinating connections between electrodynamics, gravitation, and inertia. So, I will begin with Isaac Newton, and in the most important book in the history of science, physics certainly, but I believe also of science, which is the Principia 1687. And in this book, in our notation, Newton presented his second law of motion, F equals ma, force equals mass times acceleration, and his law of universal gravitation, that the force is proportional to the product of the two masses and falls as 1 over r squared. During this school, Kai especially was discussing these two equations here in one very important problem, which is the Kepler problem. That we have the sun and the planet, and Newton himself showed that following his law of universal gravitation, the planet will describe, for instance, an ellipsis around the sun. So this is a two-body problem. Even discussed today and yesterday the three-body problems and so on. I will also consider the two-body problem, but even simpler than that. Also another problem discussed by Newton, which is just the free fall of an apple. So this is Newton's apple, and that is the experiment. Okay? Very simple in Newtonian mechanics. F equals ma, the two-body problems, the apple and the earth, and the force exerted by the apple, which is just the weight. Okay? From here to here, Newton's law of gravitation falls as 1 over r squared. But the radius of the earth is so great that from here to here, the force is essentially constant. So we have a constant force, which we call m small g equals ma. The two masses cancel, and if I obtain the acceleration, it will be the small g, which is capital G mass of the earth divided by the square of the radius of the earth. When we plug in the value of g, mass of the earth, and the radius of the earth, we obtain 9.8 meters per second squared. Perfect. No. This is only a mathematical solution of the problem. If we really want to solve the real problem here in nature, this real experiment, this is wrong. Why is it wrong? Because this is not a two-body problem. There are stars and galaxies around the Earth. That Kepler problem is only a mathematical problem. It's not the real orbit of a planet around the sun. The real orbit, we must take into account the stars around the solar system. Why? Because they are there. They are doing forces on the planet. They are doing forces on my apple. We cannot forget them. everyone forgets them in every textbook in science. But this is wrong. We must take into account the forces of the stars on my apple. Well, according to Newton's law of gravitation, we might think the force exerted by one star, let's call it Sirius, on my apple, that is negligible because the star is very far away. So it is negligible compared with the weight of the apple. That's correct. But there are many stars, not only in our galaxy, but in the whole universe. So maybe when I calculate the force exerted by all the stars on my apple, it might have the same value as the weight of the apple, and it might point upwards. So that when I release the apple, it would be floating above of my face. Okay? Who knows? We must include them because they are exerting forces on my apple. Moreover, if there are an infinite number of stars and galaxies in the universe, I believe that, then the force exerted by all of them might be infinitely larger than the weight of the apple. If I release it here, it might be shooting upwards with an almost infinite acceleration.
You say might be right.
Yes, I can try it. When I try, it falls. Yes, but I must include them. There is only one person that I know which has considered the influence of all the stars on the apple and on the planet. And this person is my greatest hero. Not Weber. This time it's not Weber. Weber is not my greatest hero. My greatest hero is Isaac Newton. He was the only one who solved these two problems, the free fall and the planetary problems, as an infinitely large any-body system. I will show here the calculations made by Newton himself. No one takes that into account in any textbook, but Newton did. He is the fascinating, the best scientist which ever had. In the Principia, he proved the most important theorem from cosmological points of view. I will read here his words. That is theorem 30 in the Principia. He considered a spherical shell and a body inside the shell. Then he proves his words. If to every point of a spherical surface there tend equal centripetal forces, decreasing as the square of the distance from these points, I say that a particle placed within that surface will not be attracted by these forces anyway. So what is the consequence of this? The force of each one is small, but it is there. But when I integrate all of them in a spherical shell, it goes to zero. Then you can go to as many shells as you wish, even to infinity. But this theorem, it applies only for central force which falls as 1 over r squared. It's not at all trivial. It would be trivial if the apple were in the center. But when it is outside the center, it's not trivial at all. So here is the correct way to solve the two-body problem. Not the two-body, infinitely many-body problem. Correct way to solve the free fall. The force exerted by the ears plus the force exerted by all the stars is equal to ma. It is theorem 30 which tells us that this force goes to zero. Then we go back to my previous slide. But it is theorem 30 that we are applying here, and also in the Kepler problem. Okay? Then we obtain this value. Well, let's go on, because I will come back to this result later on. It's essential result. What is this acceleration 9.8? It's not the acceleration of the apple relative to the ground. Why not? Because Newton applied the same problem to Kepler motion. So the Earth is not moving relative to itself. So the MA must be acceleration of the test body relative to something else. So what did Newton say? Newton said that the acceleration in his second law is acceleration relative to absolute space, which, without relation to anything external, remains always similar and immovable. These are the words by Newton. So, the free fall acceleration of 9.8 meters per second square is not the acceleration of the apple relative to the ground. It is the acceleration of the apple relative to empty space, or relative to the vacuum, which Newton did call absolute space. And in his words, it has no relation to anything external. It's not related to the ground, it's not related to the stars. So it is empty space. He gave a name. Okay? But let us move on. Now I will discuss you another topic, and then I will, in the end, come back to the free fall. For 2,000 years, we did assume that the Earth was at the center of the universe and at rest. That was Ptolemaic system. Then came Copernicus and said, no, the sun is at the center, and the Earth spins once a day around its axis and once a year around the sun. But how can you know which one of them is the correct one? Were all of us completely dumb for 2,000 years to believe that the Earth was at rest? Not at all, because we don't see any effect due to the rotation of the Earth. What we see is that the sun rising and the sun setting. Even our language is geocentric, because that's what we see, that's the phenomena. Can I prove that the Earth really spins? Galileo tried but failed with his theory of the tides, which was completely wrong. But the great Isaac Newton could prove it, that the Earth really spins, and I will discuss this subject here. There are two kinds of diurnal rotations of the Earth. The one is called kinematic or relative rotation, which takes place between the Earth and external bodies, like the stars and galaxies. A completely different kind of rotation is called absolute or dynamic rotation of the Earth. The second class produces visible phenomena on the Earth, like the flattening of the Earth, which I will discuss, and Foucault's pendulum experiment, which came after Newton. But I will discuss here the flattening of the Earth because that was considered by Newton himself. And I will try to show the connections and distinctions between these two kinds of rotations of the Earth. So I will begin with the kinematic or relative rotation of the Earth. How do we know that there is some kind of rotation? For instance, for 2,000 years, Aristotle, Ptolemy, and so on, they spoke about the rotation of the heavens, because that's what we see. Not only the sun rises and sets, but if we look at the night sky, the stars also rise and set. They make a turn once a day, just like the sun. If we are at the northern hemisphere, and we look at the sky, take a camera, press the button, and wait for 2 hours, for instance, then we will see, that's a real picture here, we will see the stars describing circles in the sky around a very specific point, which in the northern hemisphere there is a very bright star, which is not exactly at the focus, but very close. So all the stars, they rotate around a very bright star in the northern hemisphere. In the southern hemisphere, we have the similar image, but there is no specific star at the center. So, this is the kinematic rotation, how we define the North Pole and the South Pole. We connect this star to the center of the Earth, and this defines the axis of rotation. The closest point is the North Pole, here's the South Pole, and here it is the equator. All the stars rotate around this one. And we can measure how long do the stars take to make a turn. That is 24 hours. Exactly 23 hours, 56 minutes and 4 seconds, but let's approximate here to 24 hours. Sidereal period of the stars. How can we interpret this phenomena? Two ways. Either the stars spin together around the Earth, or the stars stay stationary and the Earth spins around its axis, Ptolemy or Copernicus. Both interpretations, they are equivalent. In this interpretation here, we are here looking at the Earth from above. Here it's the North Pole, and suppose that there is a wall here. So the North Pole is here, and there is a wall. And this wall is here, and it is aligned with these 4 specific stars, 2, 2, and my wall. That we take a picture of the sky. 3 hours later, we came and make the same picture, and we see that all the stars did rotate together clockwise. Okay, the 4 stars are no longer aligned with my book, but they are inclined. So that is one interpretation, that the heaven of stars rotates. Or, I can say like Copernicus, that the stars are stationary, but the Earth now rotates anti-clockwise. Okay? So these two, the kinematic rotation of the Earth is equivalent from Ptolemy and Copernicus. I forgot to, what I'm talking today is in this book, Relational Mechanics and Implementation of Mach's Principle with Weber's Gravitational Force. So they are also available in my homepage, and you can give a look. I will just make a summary during the talk today. So, the relative rotation between the Earth and the stars, we can interpret both ways, or as 2,000 years, like Ptolemy, and the modern view like Copernicus. Now, I will discuss another kind of rotation of the Earth that was predicted by Isaac Newton, which is the following. First, I will make the experiment here to show to you the effect. Here I can simulate here the Earth, but this are only 2 metal strips. They are fixed at one extremity, and at the other extremity they can move. Not here, but here it can move. Okay? So in the beginning it is spherical. So if I just make like that, I hope you can see that it flattens. Okay? The fastest I spin, the greater is the flattening. Let's suppose that in the beginning it has a radius r, that when I turn it once a second, let's suppose that it shortens so that the distance between the north and the south is just r instead of 2r. Just to give a number, okay? A very specific situation. So here, what keeps the spherical shape is an elastic force. Newton made a calculation, very difficult calculation, very difficult, and to calculate the effect which appears if the Earth spins around its axis relative to absolute space. And then the forces acting here are the gravitational force and the force due to Archimedes' principle in the fluid of the Earth, because the Earth is full of fluids, water. Then these are the words by Newton in the Principia. Very difficult calculation. The diameter of the Earth at the equator is, to its diameter from pole to pole, as 230 to 229. Very specific. And so these are the numbers by Newton, and this is the result. So this is the ratio between the equatorial, the diameter at the equator, and the diameter from pole to pole. Okay, the ratio of these two distances. And I won't show the details here. I will take 1 month, 2 months, or a year. But here is the final result of Newtonian mechanics. In our notation, it's G, capital G, and so on. But this is Newton. Newton made these calculations. So what is important here? The density of the Earth appears in the denominator. We have the universal constant of gravitation here. And in the numerator, we have the square of the angular rotation of the Earth. Rotation relative to what? Rotation relative of the Earth relative to absolute space. That is Newtonian calculation. Absolute space which has nothing to do with the stars, sun, and so on. Empty space, vacuum. But you see, here the stars do not appear here. But we have here an effect which we can measure if the Earth is or is not flattened. When Newton made this calculation in 1687, no one knew about the shape of the Earth. It took scientists, astronomers, 50 years until they could measure if the Earth was or not flattened like that. Huygens had another theory that the Earth should be flattened in the opposite direction, longer between north and south and shorter at the equator. So there was a controversy at Newton's time, and the astronomers in Picard and others in France went at great lengths to measure the shape of the Earth. Then 50 years later, they conclude that this is precisely correct. And this amount of flattening and the prediction by Isaac Newton. Two remarkable coincidences. I showed to you that we can find the axis of relative rotation by the North Pole star. Another axis of rotation is given by how is this object flattened. For instance, if I spin it like that, it's flattened in this direction. If I spin it like that, in this direction. So this axis of rotation, of flattening, this is absolute axis of rotation. They might be different from the rotation of the Earth relative to the stars, but they coincide one another. Moreover, in the previous slide, I showed to you a calculation. This is the measured value of the flattening. In order to obtain the measured value of the flattening, I need to plug in the mean density of the Earth, which Newton also determined between 5 and 6 times the density of the water. That was what Cavendish determined 100 years later and found with his torsion balance, not capital G. Cavendish never mentioned capital G, as the textbook says. Newton never mentioned capital G. What Cavendish determined was the mean density of the Earth. And Cavendish found 5.5 times the density of water. Newton had predicted 100 years later between 5 and 6. Newton is fascinating. Moreover, I need to plug in here a very specific angular rotation of the Earth. To obtain the measured value, this angular rotation must be once a day. Okay? So But in Newtonian mechanics, these two facts are coincidences, because there is no relation of the stars on the flattening of the earth due to Newton's theorem 30. The influence of all of them cancels on the earth. So the earth might be flattening like that, and the stars might be spinning like that around the earth. It might be. There is no connection between the two facts. So this is a remarkable coincidence, which, according to Ernest Mach, suggests that somehow the distant objects, stars and galaxies, so on, are the ones responsible for this effect. Let me go on. This Ernest Mach, Austrian physicist, he published a most influential book, The Science of Mechanics, 200 years after Newton. In this book, he said, the principles of mechanics can be so conceived that even for relative rotations, centrifugal forces arise. He also had the following idea. Try to stop the earth and rotate the heaven of fixed stars, and then prove the absence of centrifugal forces. This book by Ernest Mach caused a huge influence in a very specific scientist, Albert Einstein. In his autobiographical notes, Einstein said that he read this book when he was at school, high school, and it caused a deep impact upon Einstein. Einstein devised his general theory of relativity in order to implement Machian ideas. He didn't succeed, but all his guiding ideas were due to this book by Ernest Mach. Now I will discuss with you two phenomena which I want you to think about. About the shape of the earth that we are spinning. So, as I said, the earth spins once a day and it's flattened. Very little. Here I am exaggerating. The amount of flattening is 0.4%. Here it is huge, because here I spin very fast, once a second. But the earth spins once a day, so it's very small flattening, 0.4%. But here I can do it very visible, okay? If we could stop the earth is full of water, the earth would become spherical. Let's suppose that I am looking at the earth from above, and that it spins once a day clockwise. Now I ask you a thought experiment, a Gedanken experiment, okay? Now I stop the earth, it is stationary, and now I will spin. Superman goes there and spins the whole universe around the axis of the earth, once a day. So that's the question. What will be the shape of the earth? You might say, oh, it's the same thing. Then I can ask you this experiment here. I spin it really once a second, and it becomes that amount of flattening. Now I let it here at rest in this table. We are all at rest. Then comes Superman, goes there and spins the whole universe, all stars and galaxies around this axis, once a second, not once a day. What will be the shape of these metallic strips here? I want you to think about it. I don't will ask you the answer, but I will give you 1 minute to think about. No one knows, and no one will never know, because these are thought experiments. So we don't need to be afraid, because there is no wrong answer and no right answer. But think about. So anything can happen. We can explode. Anything can happen. But I will give you 2 options. Either the earth will remain spherical, as when it was at rest, or the earth will be flattened. How much flattened? 0.4%. Or, in this experiment here, when I turn it once a second, the distance between North and Pole instead of 2r is r. Now I let it here at rest. Superman goes around here, spins the whole universe once a second. Two options. Either it will remain spherical, or it will become flattened, so that the distance between up and down here will become r. Think about each one of you. Make a choice. Even if you don't know physics, most of you are mathematicians, just make a guess. Your intuition. Who doesn't have intuition? Don't matter. Just pick up one choice. Either spherical or flattened. Then I will show you the answers by Newton, Einstein. Make each one of you your choice. I will wait here. Go on?
Yes.
Okay, I will not ask you. So, and later on you can change your mind. Don't worry. And even no one is right or wrong. We will never know. It's impossible to rotate the whole universe once a second. But it is very important that you make your own decisions. Because, as I will show now, depending on your choice, you are a follower of Newton or a follower of Ernst Mach or of Einstein, because each one of them gave a different answer. According to Newton, do you remember theorem 30? The force exerted by all the stars. Newton didn't know galaxies, and put in galaxies, but doesn't matter. The force by all of them on each molecule of water is zero. The same when the universe is spinning, because Newton's law of gravitation does not depend on velocity. So the force will remain zero. So even when the universe is spinning around the Earth, it will not create any centrifugal force. Einstein, in his general theory of relativity, he wanted the Earth to become elliptical, because that is the Machian idea. But in general theory of relativity, I won't show the details here, there are real centrifugal force. But in the length steering calculation, it appears also a force along the axis of rotation. And the Earth would become this, I don't know the shape of this, but it will be flattened and like I don't know the name. I need to look at that. He didn't want that. He wanted this here. So this is the answer given by Ernst Mach, and I will show in a moment what comes out of relational mechanics. Okay? But you see, if one of you did choose this one, you are Machians. If you choose this one, you are Newtonians. It's not bad. Newton, to me, is the greatest of all scientists of all time. I disagree with him in this respect. But it's not bad. It's wonderful. And if you are crazy, you go with Einstein. Because it's a pity that you cannot do the experiment, because this would never happen, sure. This here would never happen. Either this or this, no doubt.
But
the other one is, forget it. But
the lens steering effect was measured.
Sorry?
The lens steering effect was measured. Not obviously in the rotating universe.
So maybe who is crazy is myself. So maybe you are right. Maybe Einstein is right after all, as always. Now I will ask you another question. With our other friend, which Urs showed his picture yesterday, Carl Neumann, the son of Franz Neumann. He has his potential Lagrangian for Weber, excellent and so on, but he also did work on the foundations of mechanics. And he has a very nice book about the Galilean principles and so on. And in this book, he's made a most fascinating question. what would be the shape of the Earth if all other astronomical bodies were annihilated? Not go away, from far away. We make like that, they disappear from the universe. This is even more Gedanken than the previous one, because the previous one, the stars are still there. Now it disappears with all of them. Only the Earth remains. If you wish, we can make a Floer homology, and we can begin with the present universe, in which it is 0.4%. Then I decrease to half of the number of stars and galaxies, and I ask the same question. Then we have only, because when I have half, the Earth is still spinning once a day. Then I have only 10% of the stars and galaxies, and the Earth is still spinning once a day. So the shape will change or not, until we reach the final situation in which the Earth is alone in the universe. I will also give you two choices. The Earth can explode, but either it will remain ellipsoidal, or it will go back to spherical when it is alone. So I give you a minute to think about. Later on I will show you what Newton and Einstein said. Don't worry about your choices. You can change that later on. For instance, in the intermediary cases in which you have half of the number of stars and galaxies, I'm supposed that the Earth is always once a day, okay? Only the number of stars is changing here, stars and galaxies. So try to pick up one of these two choices. Either it will remain ellipsoidal or it will become spherical. Okay, made your choices. So I will now show you the answers by famous people. In this case, Einstein's agree with Newton. The same theorem 30 is valid in general theory of relativity. The force exerted by a stationary spherical shell on internal point is zero. So we can increase spherical shells or decrease them, that will not affect us here. So theorem 30 for stationary shell is valid also in general theory of relativity. According to Ernst Mach, the Earth should become spherical. Why? Because if the Earth is alone in the universe, we cannot even talk about rotation. Rotation relative to what if it is alone? So there is not even philosophical meaning in this question to say that the Earth alone spins, unless there is this empty space. But if you are a Machian, there is no empty, it makes no philosophical sense to say that this point moves relative to empty space. It can only move relative to matter. It gets closer or far away from the wall. There's a real motion, physical motion. So according to Ernst Mach, if the Earth is alone in the universe, it cannot rotate, it cannot move, it cannot do anything. Therefore, no effects due to its pseudo-rotation might appear. So somehow, the amount of flattening should depend on the amount of stars, of matter in the universe.
You know, there is something that for me, it's, of course, it's just a remark. The Earth is not a point in the universe. It's a distributional mass. It's not.
Yes,
in some sense.
It is. It has a volume.
No, exactly. So the point is to be alone in the universe.
Yes, but it
It's
could be
a lot of mass interacting itself. So the gravitation is still hold
yes,
Earth together.
Yes. But the question is, will it be flattened or will it be spherical?
For me, it be flattened, no doubt.
Okay, so you are a Newtonian, or if you prefer, you are an Einsteinian.
And I don't
But-
understand even the argument of the other argument, because that's the point. The Earth, we can measure the flattening of the Earth
Yes.
Because it's not a single object. It's a
I
collection.
know, but the question is, does this flattening depend or not on the amount of matter in the universe?
Yes, I understand. Just make
Let me just go on, let me just continue. Now, so I showed you the problems I'm dealing with, okay? Now, finally, I go back to my second greatest hero, Weber, okay? Now, that's the book which is with you, Relational Mechanics and Implementation of Mach's Principle with Weber's gravitational force, which is available in my homepage, in English and in Portuguese. What is relational mechanics? It's based on two postulates. Instead of saying F equals ma, we say that the sum of all forces acting on anybody is always zero in all frames of reference. That's crazy. Yes. Instead of utilizing Newton's law of gravitation, we apply Weber's law for gravitation. But as Joe said, when I release my apple, it falls down. How can I say that the sum of force is zero if we see that the apple is falling? In relational mechanics, I will say that the sum of the forces on the apple is zero all the time. When it goes up, down, hits my hand. If I were a worm in the apple, eating the apple, I would also say that the force is zero during all the time, during all these collisions and cusps and things like that, and so on and so on and so on. Everybody, if I were in a rocket, spinning rocket, I would also say that all the time the force on the apple would be zero.
Yes, what I'm confused with one thing. This F is the F that you should equal to M times A, or is just...
No. I come that in a minute. So, before I solve the free fall of the apple, I will show to you here the main calculation of relational mechanics. Do you remember? According to Newton, if I have a spherical shell and a particle inside the shell, the force goes to zero. No matter the rotation of the shell, and no matter the position of the test particle inside the shell, no matter the velocity of the test particle inside the shell, no matter the acceleration of the test particle inside the shell. Why not? Because Newton's law of gravitation does not depend on velocity and acceleration. So the force is always zero. Even, for instance, this is my spherical shell, the walls here in this room. Even when I make like that, my hand with the apple, the walls will not exert a net force on the apple. But that, remember, that is a theorem which is valid only for this first component here of the force, which is a central force which falls as 1 over r squared. The second component also is central force falls as 1 over r squared. So it will also apply to the second component. But the theorem of Newton does not apply to Weber's third component. Because here we have an r and then r squared, and they cancel. The last component falls only as 1 over r. So the theorem of Newton does not apply to Weber's law. What is, and then we need to do the integration. To know, it's not obvious that it will be zero. And when we do the integration, I won't show the details, it is in my book. The result is that the force is no longer zero. If I try with my hand to accelerate the apple to the right, the walls of this room will make a small force to the left, minus a constant phi ma. This constant phi depends on the radius of the shell, on the mass of the shell, and of Weber's constant c, or light velocity, as I'm utilizing it here. And the force is opposite the acceleration of the apple or the test particle relative to the shell. As I said, if I accelerate with my hand the apple to the right, the shell will exert a small force to the left, which depends on the amount of acceleration. Okay? Now that I have this result here, then I can solve the free fall of the apple.
Excuse me. There is a theorem by Ostrogradsky, this is the Newtonian mechanics,
Yes.
that basically says that at least if you put such a system into a least action principle, there will be instabilities. Because the Lagrangian will depend on, if you put it in Lagrangian form,
Yes.
or in Hamiltonian form, it will depend on acceleration. Or there is no least action description here.
And so what's your point?
I'm asking.
I don't know the answer.
Okay.
So,
I mean, is there, it could be that there is no least action principle for this.
maybe.
But if there
we
is, then it's unstable.
didn't need to look for, I don't know. I need to think about this problem. So, now I will discuss once more the free fall of the apple. What are the forces acting on the apple? The force of the earth, sum of force equals to 0. Force of the earth acting on the apple and force of the stars and galaxies acting on the apple. According to Newtonian mechanics, this term here did go to 0. But with relational Weber, it doesn't go to 0. So I need now to, I have here for a spherical shell. Now I need to integrate for the whole universe. Okay? So I will integrate that result for the whole, so instead of a small phi, I will come with a capital phi, which is the result of this integration. So I integrate for a shell and then integrate to infinity. So it will be minus capital phi ma here. This is what we get. So in a sense, we are deducing, ragazzo, Newton's second law of motion. We are deducing minus ma to the left side. This is a real force of gravitational origin exerted by the system of stars and galaxies acting on my apple. So that's the reason why the mass appearing here is the gravitational mass. It's not the inertial mass. I'm not discussing this here, but in Newtonian mechanics it is an inertial mass. When we deduce that with relational mechanics, we obtain the same kind of mass which appear here, because they are being deduced from the gravitational interaction. And the acceleration here is no longer relative to empty space. It is the acceleration of the apple relative to the set of distant stars and galaxies. Then I can put this term to the right-hand side, cancel the two masses, and then I obtain the acceleration, which will depend on the ratio between this hg by capital phi. And now, when we do the integration, so it will appear the mean density of matter in the universe and either the Hubble's radius, for instance. When you do that, you obtain the constant of universal gravitation. But it's no longer a constant now. It is a function of the mean density of matter in the universe and of Hubble radius. This fact here was known by Dirac. That is one of the bases of his theory of great numbers, that many ratio of force 10 to 39 and so on. That should not be a coincidence, and so that is one of those ratios here. It was known already by Dirac. Here we are deducing this result. Here, it is the whole of relational mechanics. In a sense, we are deducing ma from Newton. We are not beginning with that. We begin with the sum of all forces being 0. And we show, in general, that the force exerted by all stars and galaxies on any body, when this body is accelerated relative to the universe, is minus ma. So you pass this, you come back to Newton's second law. So the previous slide presents the essence of relational mechanics. We begin with the postulate that the sum of all forces acting on any body is always 0. Then we deduce an expression analogous to Newton's second law of motion, this one here. In this equation, the capital F here represents the usual forces acting on the test body. The force of the earth, the normal force exerted by the stable, friction, and so on, a spring, and so on, if discharged, a magnetic field, and so on, and so on. And this component here, minus MA, represents the real gravitational force exerted by the set of distant galaxies acting on the test body according to Weber's law applied to gravitation. The mass appearing here is the gravitational mass of the test body. That is, it is not the inertial mass as in Newtonian mechanics. The acceleration appearing here is the acceleration of the test body relative to the frame of distant galaxies. It is not the acceleration relative to empty space, to the vacuum, or to Newton's absolute space. Okay? Now that I showed how to solve the free fall, so force of the Earth plus force of the galaxy equals to 0, I will solve the shape of the Earth. Okay? In the same situation. What are the forces acting on any molecule inside of the Earth? It is the force of gravitation due to the other portions of the Earth. It is the force due to Archimedes' principle, due to the gradient of pressure of the water, and the force exerted by the distant universe, acting on any molecule of the Earth. Before that, I will make a very general calculation here. I showed to you what would be the force exerted by the shell on an internal body. Here I am showing the force exerted by a spinning shell on an internal body. According to Newton, that is always 0. Always 0. But according to Weber, that's no longer 0. The previous result was this one. If I now let the shell spin, there will be these two extra terms. For those of you who remember mechanics, this is what we call centrifugal force. This is what we call Coriolis force. But these are no longer fictitious forces. These are real forces, gravitational forces, exerted by the spinning shell on an internal test body. That comes out exactly like that from Weber. Exactly. Newtonian, that comes 0. In Einstein, that does not come out like that. There is a kind of centrifugal force, but the coefficient is not like here, 1 and 2. It is 1 and 5 in general relativity theory, the Lens-Thirring effect. And moreover, in relativity, there is a third component which points along the axis of omega. I will not show it here. But it cannot be right, because it must be 1 and 2. So now I will go back to the shape of the ears. So now I have the ears spinning with omega E, and I am calculating here a very general situation in which Superman already put the whole set of stars and galaxies spinning with omega U around the axis of the Earth. And then I will calculate what should be the flattening according to relational mechanics. Before that, I show you once more the result by Newton. The result by Newton, the stars don't appear here. So I can put omega U to any value I wish. That will not affect the amount of flattening. I can disappear with the stars. The Earth can be alone in the universe. It would be flattened by the same amount. Even an Earth alone in the universe would be flattened according to Newton by the same amount. And it would make sense to talk about the rotation of the Earth, even in empty space, because in Newton, the Earth might be moving relative to nothing. That is his absolute space, which has no relation with anything external. To Mach, that would make no sense. But to Newton, that does make sense, and his result does not depend on the amount of stars and galaxies, how fast they spin. I can increase or decrease the number of stars and galaxies. That will not change the flattening of the Earth. Now I won't show the details of the calculations, they are in the book. I will just show you a comparison of the Newtonian result with the result from relational mechanics. Okay? These are the result by Newton, and this is the result according to relational mechanics. The first difference, instead of only the angular rotation of the Earth, what appears here is the relative rotation between the Earth and the universe to the square, just to the square like here. In Newtonian mechanics, it did appear a capital G, the universal constant of gravitation. Remember that according to relational mechanics, this should depend on the mean density of matter in the universe and of Hubble's radius. When we plug in these values, the mean density of the matter of the universe appear in the numerator. The mean density of the Earth, 5.5 times the density of water, comes here in the denominator. And here is Hubble's constant, which is related with Hubble's radius. Okay? So the results are here and here, they are different. But when we plug in the values of these constants, we obtain the same amount of flattening. But the interpretation is completely different. In particular, in the usual calculation, the universe is at rest and the Earth is spinning. Then we go back to Newtonian result. In the thought experiment, the first one which I told you, the Earth did stop. And now the universe rotates once again. But as there is a square here, it will come back the same result, the same amount of flattening. Okay? And now I can quantitatively make that Floer homology, that I go decreasing the mean density of matter in the universe. The density of the Earth is 5.5 times the density of the water. The measured mean density of matter in the universe is 1 hydrogen atom per cubic meter. Okay? When you put that number here and the known value of the Hubble constant, you obtain this result here. But now I can, in my thought, make it half as dense. When I decrease the number of stars and galaxies by half, the amount of flattening decreases. Instead of 0.4%, it will be 0.2%. When in the limit, when I disappear with all the stars and the galaxies, this whole star goes to 0. When it goes to 0, this ratio becomes 1. The Earth becomes spherical. Okay? So this is a quantitative implementation of Mach's principle. Relational mechanics leads to two main consequences. One, the flattening of the Earth depends on the relative rotation. Relative rotation because of this omega of the Earth minus omega of the universe. It's not only the rotation of the Earth, it is between the Earth and the universe. Depends on the relative rotation between the Earth and the set of distant galaxies. The Earth will be flattened not only in the Copernican worldview, the Earth spinning daily, daily relative to a background of stationary stars and galaxies, but also in the Ptolemaic worldview, a stationary Earth surrounded by a set of stars and galaxies spinning together once a day around the Earth's north-south axis. So, the rotation of the Earth, the flattening of the Earth, was Newton's argument that the Copernican system was the correct one. Because in Newtonian mechanics, the Earth would not be flattened if it did remain at rest in the universe and the stars did spin once a day around the Earth. Kinematically, we would see the same thing. The sun rising and setting, the star rising and set in both systems. But in only one of them, the Earth is flattened, in Newtonian mechanics. In relational mechanics, this is no longer a proof, because it happens in both worldviews. Moreover, the numerical value of the flattening, this 0.004, depends now on the amount of external bodies around the Earth. If we could make the average density of mass in the universe go to zero, for instance, by annihilating all stars and galaxies, then the Earth would become spherical. We can now answer Carl Neumann's 1869 question quantitatively as follows, according to relational mechanics, obviously. According to Newton's mechanics, it will remain flat. The shape of the Earth would be spherical if we could annihilate all other astronomical bodies. But we cannot make the experiment, so we don't know who is right, who is wrong. But we have a mathematical theory which implements quantitatively all these fascinating ideas, philosophical ideas. So, conclusion. Relational mechanics implements quantitatively Mach's principle. The flattening of the Earth, I didn't discuss here Foucault's pendulum, it's fascinating, but another day we talk about that, are due to a real gravitational interaction of anybody on the Earth with the set of distant galaxies. These phenomena take place not only with the Earth spinning once a day relative to a stationary set of galaxies. We should have here not only, but also with the set of galaxies rotating daily around the north-south axis of the Earth. The Ptolemaic and Copernican worldviews are now equivalent, not only kinematically, as was always known, but also dynamically. Thank you.
Okay, let's jump out. Do you have any questions? Yes, please. Alan, what's your name, please?
Giorgio Torrieri, I'm from RGW, from the Physics Institute. Just as a...
He is my colleague at
Yeah,
the Physics Institute.
we're nearly neighbors, office neighbors. Just as, I mean, the theorem about the fact that forces from distance, even though the universe is infinite, and even though the universe is infinite, all forces cancel out, and so the apple falls and doesn't rise. This is indeed a really beautiful thing, in my opinion.
Yes, this is the theorem 30 from Newton.
Yeah, exactly. And sort of the heart of the matter there is that the fundamental assumption there is that forces are vectors.
Yes.
And vectors cancel out because of isotropy. In Einstein, this assumption fails to hold because you don't have vectors, you have pseudo-vectors and time is dilated, etc. And in my opinion, this is a beautiful theorem because this is a very simple explanation of what the difference is. In Newton, you have zero forces. In Einstein, you do actually have a net, if you want to call it time dilation, but basically the universe either contracts or expands. In a sense, Mach's principle also goes away because there is no such thing as an asymptotic, this infinite distribution of galaxies. Either everything contracts or everything expands. There is no static solution. And in fact, when Einstein saw it for the first time, he was like, this is obviously rubbish. I will add a cosmological constant to reach an unstable equilibrium. Except experimentally it's not rubbish, because the universe does seem to be expanding. I mean, some of these things we cannot annihilate the galaxies, we cannot annihilate, we cannot make them rotate, but there are things we can do. I mean, the lens steering effect has been measured to pretty high precision with satellites, and the Einstein thing, it's a very counterintuitive, but mathematically it's a very straightforward prediction of the expansion of the universe, which we see. I mean, we see it in the galaxies.
So maybe the conclusion is that, as always, Einstein has been right and continues to be right.
Yeah.
It's a possibility.
No, he was wrong, but his theory was right.
Yes, even that's fascinating. Even when Einstein makes mistakes, like with the cosmological constant, he even turns out to be right. It's amazing. It's a miracle to me. Yes.
Another question is,
Yes?
no, if you have this static, the galaxies, this
Yes.
very static, not rotating at all, do you get the Newtonian mechanics in this situation, or you get something different? Because you said then you use
Let
the
me show
principle-
to you. I will show to you. That's what we get. Stationary galaxies. I'm studying just the free fall. Just the free fall. Okay? The force of the Earth plus the force of the stars is equal to 0. Then I show with relational mechanics that the force of the stars is minus capital phi ma. So is that Newtonian mechanics? Not. It's similar. Why similar? Because the mass appearing here is gravitational, while in Newtonian mechanics it is inertial. The acceleration is not the same. In Newtonian mechanics it is acceleration relative to absolute space, which is empty space or the vacuum. Here it is the acceleration of the apple relative to the background in which the stars are at rest. But amazingly, as I said before, there is this coincidence in classical mechanics that the best inertial system we have is the one in which the stars and galaxies are at rest. But here we give an explanation for that, because only in this frame the force by the stars and galaxies comes out like minus ma. If I make the calculations with the universe spinning, the force is no longer minus ma. It appears other component. So my question is the same as Newtonian? No, but you do get 9.8 meters per second square as the acceleration of the apple.
No,
But the interpretation is not the same.
But for instance, if you have now this, everything is moving uniformly now,
Yes.
constant uniform velocity with respect to this
Yes.
stars outside.
You will also obtain this result here.
Is invariant under uniform translations.
Yes, but not for rotations.
I understand, rotations are different. Now I got it.
Okay, further questions? Okay, then let's thank André for his
Thank you
series of
very much.
very inspiring lectures.